Noir plasma chrome bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.
This website makes learning so easy. I found all my resources here.
Like what you share.
String theory suggests that the universe is not made of particles, but of tiny, vibrating strings of energy, harmonizing to create all reality.
Imagine a master translation manual, a sort of cosmic Rosetta Stone that successfully bridges the two most radically incompatible worlds in all of physics. On one side, you have the macroscopic realm of gravity. On the other, the microscopic realm of quantum mechanics. Welcome to this explainer. Today, we're taking a really deep dive into one of the absolute most profound breakthroughs in modern theoretical physics. We're looking at the anti-de Sitter/conformal field theory correspondence, or as it's almost always called, ADS/CFT. Now, I know that concept sounds totally intimidating, but we're going to unpack exactly how it acts as a holographic dictionary for the entire universe. Okay, let's dive into this. First, we'll cover the background of these two clashing worlds, followed by an overview of the holographic duality itself. Then, we'll look at applications for both quantum gravity and quantum field theory. Finally, we'll trace the history of the idea and look at some future generalizations. So let's start right at the core definition. The ADS/CFT correspondence is a conjectured mathematical relationship between two very different things. On one side, you have ADS, which stands for anti-de Sitter spaces. Basically, these are geometries used in theories of quantum gravity, usually formulated in string theory. On the exact opposite side, you have CFT, or conformal field theories. These are mathematically well-behaved quantum field theories, really similar to the ones that describe elementary particles. And this brilliantly illustrates what physicists call a strong-weak duality. See, when the math on the quantum field theory side becomes strongly interacting and just impossibly difficult to solve, the math on the gravity side becomes weakly interacting and super tractable, and vice versa. It is literally a dictionary that lets you translate a totally impossible math problem into a solvable one. Section 1. Background. The two worlds of physics. To really appreciate why this mathematical dictionary is so revolutionary, we have to look back at a historical conflict. It's a tale of two distinct worlds. On the left side of the ring, we have gravity, governed by Albert Einstein's 1915 general theory of relativity. This is a classical physics framework where space-time is this smooth, continuous, deeply predictable geometry. On the right side, we have quantum mechanics, which describes all the other fundamental forces. This is a microscopic world of particles and fields governed entirely by probabilities and uncertainty. And for decades, physicists have just been banging their heads against the wall trying to unify these two completely incompatible mathematical frameworks into a single cohesive theory of quantum gravity. Now, a major attempt to unify these worlds is string theory, which proposes that elementary particles are actually tiny, one-dimensional strings. But there's a pretty massive catch here. String theory requires extra dimensions, 10 or 11 in total, just for the math to be consistent. So why don't we see them? Well, think of the garden hose analogy. If you're looking at a garden hose from way down the street, it just looks like a flat, one-dimensional line. But as you walk closer, you realize it has a second dimension, its circumference, wrapped tightly around it. This process, known as compactification, curls up those extra dimensions of string theory so tightly that we simply don't perceive them in our everyday four-dimensional world. Section 2. Overview. The holographic duality. So, keeping those hidden extra dimensions in mind, let's actually visualize the specific geometry that makes this duality work. Let's build anti-de Sitter space, the ADS part of our correspondence. Step 1. Picture a hyperbolic disk. This is a space where the distance between points is so distorted compared to standard geometry that the outer boundary is actually infinitely far away from the center. Step 2. Imagine stacking a bunch of these disks right on top of each other, where the vertical axis going up represents the progression of time. Step 3. You're left with this solid cylinder. This 3D cylinder represents anti-de Sitter space, but pay super close attention to the surface, the boundary of this cylinder, because that is where the magic actually happens. The real hook of the holographic duality is right here. The correspondence states that a quantum gravity theory operating completely inside the interior of the cylinder, what physicists call the bulk, is exactly mathematically equivalent to a conformal field theory operating only on the outer boundary. It's wild. Just like a flat 2D hologram encodes all the 3D information of an object, the lower dimensional boundary perfectly maps to the higher dimensional interior. Every single particle, every interaction in the bulk has an exact mathematical counterpart on the boundary. So we have this wildly elegant, totally mind-bending mathematical translation between a higher dimensional gravity interior and a lower dimensional quantum boundary. But you're probably wondering, how is this actually useful for understanding our physical universe? Section 3. Quantum gravity applications. Solving black hole paradoxes. Let's look at the very first major payoff of this dictionary, starting over on the gravity side of the equation. Usually, in quantum field theory, physicists calculate probabilities using Feynman diagrams to map out point-particle interactions. But honestly, this really only works when those interactions are weak. String theory completely lacked a full non-perturbative definition for when strings were strongly interacting. But because of this duality, physicists can now completely define string theory, at least in a universe that resembles anti-de Sitter space. Just by looking at the dual quantum field theory on the boundary, it finally gave physicists a rigorous mathematical foothold. And having that foothold, that allowed us to tackle one of the greatest, most frustrating mysteries in all of physics, the black hole information paradox. Back in 1975, Stephen Hawking calculated that black holes aren't actually completely black. They emit a faint radiation and eventually evaporate away to nothing. But his calculation heavily implied that all the quantum information of the stuff that fell into the black hole is permanently destroyed. This completely and violently contradicts the unitarity postulate of quantum mechanics, which is a core rule stating that physical systems must always evolve in a way that preserves information. So the crucial takeaway here is exactly how the ADS/CFT correspondence resolve this paradox. If you place a black hole in the interior of our anti-de Sitter cylinder, it corresponds exactly to a configuration of ordinary quantum particles living on the boundary. Since we know for an absolute fact that those boundary particles obey the standard rules of quantum mechanics and preserve information, the dual black hole in the interior must also preserve information. The math quite literally demands it. In fact, this mathematical proof was so convincing that in 2004 and 2005, Stephen Hawking publicly conceded his bet on the paradox, agreeing once and for all that black holes do not violate quantum mechanics. Section 4. Quantum field theory applications. Translating the quantum world. Now let's flip this script entirely and see how gravity math can actually solve impossible problems in the quantum world. In massive particle accelerators, like the relativistic heavy ion collider, scientists collide gold or lead nuclei to create a trillion-degree state of matter called a quark-gluon plasma. It's very similar to what the universe looked like milliseconds after the Big Bang. The standard quantum math to describe this is practically impossible to solve. But using ADS/CFT, physicist Dam Tang-sun and his collaborators actually translated the plasma into the math of a 5-dimensional black hole. By studying the black hole, they accurately predicted the plasma's shear viscosity to entropy density ratio would be a universal constant, the reduced Planck constant over 4 pi times the Boltzmann constant. They also estimated a jet quenching parameter of around 4 GeV squared per femtometer. These gravity calculations mapped shockingly well to the real-world experimental data of quantum plasmas. And the applications even reach far into condensed matter physics. Experimentalists create these artificial superfluids, which are totally frictionless liquids, by pouring ultra-cold atoms into a lattice made of lasers. When they crank up the intensity of the lasers, the fluid suddenly halts, completely freezing into an insulator. The totally bizarre way these atoms slow down, which depends heavily on the Planck constant, was actually modeled and understood by translating the fluid's properties into a dual description of a higher dimensional black hole. Just think about that for a second. It is simply astounding that a puddle of liquid in a lab can be mathematically modeled using the physics of a black hole in higher dimensions. Now, to be totally fair, it is vital to note that this theoretical approach definitely has its critics. Prominent physicists like Larry McLaren have pointed out that the specific, perfectly symmetrical field theory used in the most famous ADS/CFT example, n equals 4 supersymmetric Yang-Mills, is absolutely not the same thing as quantum chromodynamics, the incredibly messy theory governing our actual real-world strong force. It has no mass scale and no confinement. And Nobel laureate Philip W. Anderson similarly warned against just blindly applying this to condensed matter. He noted that real-world problems involved preferred coordinate systems and crystal lattices. They aren't perfectly conformal. It's a great reminder that while the math is a perfect translation, the idealized universes it models don't always perfectly match the messy one we actually live in. Section 5. History. The path to discovery. To really understand how we arrived at this mind-bending correspondence, let's look at how these ideas stacked up over the decades. Back in 1974, Gerard Hooft started noticing analogies between string theory and nuclear physics when looking at limits where the number of color charges goes to infinity. Then in 1975, Hawking discovered black hole radiation, completely kicking off the information paradox we talked about earlier. Fast forward to 1993, and Hooft alongside Leonard Susskind proposed the holographic principle, this crazy idea that the information inside a volume of space is actually proportional to its surface area, very much like a black hole's event horizon. All of these separate threads finally culminated in late 1997 when physicist Juan Maldacena officially proposed the ADS/CFT correspondence. And let me tell you, the impact of Maldacena's 1997 paper just cannot be overstated. It was an absolute game changer. By 2015, his paper had garnered over 10,000 citations. According to physicist Alexander Polinakov, Maldacena's work opened the floodgates, easily making it the most highly cited article in the entire field of high-energy physics. It finally provided the concrete mathematical realization of the holographic principle that theorists had been desperately searching for. Section 6. Generalizations, the future of the duality. So where does theoretical physics actually go from here? Well, theorists are currently generalizing the math in a few incredibly fascinating directions to try and fit our messy reality. First, they're studying 3D gravity. This is a simplified space-time with just 2 spatial dimensions and 1 time dimension, linking it to conformal field theories with monster group symmetry, which actually eliminates the need for full string theory altogether. Second, and probably most importantly for us, they're developing DSCFT, or de Sitter space. Remember, anti-de Sitter space isn't expanding, but our actual universe, it is actively accelerating its expansion. It has a positive cosmological constant. Theorists like Andrew Strominger are working right now on adapting the duality to a de Sitter background so we can study the cosmology of our early universe. Finally, there's Kerr-CFT, which shifts the focus far away from theoretical, perfectly spherical black holes to modeling the extremal, rotating astrophysical black holes that actually exist out there in our night sky. All of which leaves us with a final, incredibly profound question. Will we ever find the ultimate holographic dictionary for the exact universe we actually live in? The ADS/CFT correspondence definitively proved that the boundary between the smooth, classical curves of gravity and the pixelated, probabilistic static of quantum mechanics is just an illusion, that one can be perfectly translated into the other. We might not live in an anti-de Sitter universe, but the fact that a holographic translation manual exists at all strongly suggests that the fundamental code of reality is far more interconnected and far stranger than we ever dared to imagine. Thank you so much for joining me for this explainer. Keep questioning, keep learning, and I'll catch you in the next one.
Like what you share.
Noir Plasma Chrome Bleed. Unlocking knowledge, inspiring innovation, empowering curious minds.